Carolina, Charlotte. And is the screen sharing on? Okay, great. So that's okay. So please go ahead. Thank you.
Good morning, everyone. Thanks for the invitation. And today I'm going to talk about these entropic barriers and dynamical coarse-graining by the Zwanzig formalism. And this is a joint work with my collaborator, Thomas Hudson from University of Warwick. So I would like to first briefly talk about the motivations of this project, and then I will briefly introduce the Zwanzig framework for overdamped Langevin dynamic system. And then I will start with a one-dimensional toy model with a simple Zwanzig projection. And then I will talk about some ongoing work which we improved the Zwanzig projection and got improved result. And then finally, I will give you some conclusions. So the motivation is, okay, we know that for high dimensional models, it's kind of impossible for us to fully capture all the resolutions. For example, we all know that in order to run MD simulation, the time step is restricted to around 10 to the negative 12, and the best time scale we can reach is about 10 to the negative 6. So it's far below the time of the event of interest, usually happen around 10 to the negative 3 or even of order 1. Therefore, we need to reduce the high dimensions to low dimensional models. So such as the tools we can use such as coarse-grained methods. And the idea of coarse-grained methods, for example, if we are interested in, for example, some defect, then we will apply small fine resolutions to this interest region. And away from this region of interest, we will apply the coarse-grained model. And that's the idea of coarse-grained method. And there are many ways to apply the idea of coarse-graining. For example, we can use multi-scale coupling method. The idea is we have a fine scale model, for example, atomic model, and an empirical continuum model. And then we combine these two together, we will get a multi-scale coupling method. And multi-scale coupling methods are mostly empirical. And in other words, the coarse-grained model you are applying should be consistent with the underlying atomic model. And the other type of coarse-graining approach is the bottom-up coarse-graining. So that is, we have the first principle model. And from the first principle, we coarse-grained from the bottom-up scale. And the challenge for this approach are, for example, how to select the right coarse-grained variable. And then once we determine these selected variables, how can we derive effective equations based on these coarse-grained variable? And then how can we implement these effective equations? And here I just list a few coarse-grained methods from mathematical community. So I know we have a lot of experts in this panel, and let me just skip the little review here. You can find these references from our work, which I will given in the next slide. And I would like to mention that most of these coarse-grained methods, they focus on to overcome energetic barriers. And very few of them aim to overcome entropic barriers. And here I give a toy example to compare the energetic barrier and the entropic barrier. So energetic barrier means usually we have two energy wells, and the wall between these two energy wells are very high. So the system have to overcome this high wall. This is called energetic barrier. And for entropic barrier, it's slightly different. So in other words, the transition paths are constrained to certain paths. For example, in this example, the system are more likely to transit from one well to the other through this energy path. So that's called entropic barrier. And we would like to derive a coarse-graining model which overcome this entropic barrier. Okay, and so the tool we are going to apply is the Zwanzig formalism. So this is because when we want to overcome the entropic barrier, the memory term or the communication between the coarse-grained environment and the fine environment are very important. That's why we need a Zwanzig formalism in order to keep this communication. And we will demonstrate the idea for a very simple example. And what's more important is our methods are based on stochastic differential equations. And most existing works for Zwanzig are based on ODEs. And you can find some references from this paper, which is done by me and my collaborator. Okay, so let's start with the overdamped Langevin system, which is given here. And this system is ergodic with respect to the Gibbs measure. And we define the coarse-grained variable via a linear mapping G, and an intuitive way to derive the coarse-grained dynamics is to get the dynamics for G. And we can, for example, apply the Ito's formula in order to get the dynamics for G, which is given here. And we see that this system, this dynamics is not closed because we still have the dependent on xt within the dynamics. And we want to get a closed equation for GT. And so on this slide, let me briefly introduce the idea of Zwanzig projection. So the Zwanzig projection is defined via the conditional expectation with respect to the Gibbs measure, which is given here. And it's easily to verify that this P operator is linear and it's orthogonal projection. And then we can apply this Zwanzig projection to the evolution of G and then obtain a closed equation for G. So basically, the idea is we can replace this part, which is not closed for G, by the projection of the evolution. And then Zwanzig formalism can be viewed as a study of error that committed by replacing the true evolution by the projection of the evolution. And more precisely speaking, let me give you an example for ODE. This can be also found in Charlie's book, which is given here. So basically, this is the evolution of the true ODE. And because the Zwanzig projection is orthogonal, so we can decompose the ODE into two parts. And apply the Duhamel principle, we can further get the three parts representation of the evolution. And the first part denotes the main change within the coarse-grained variable. And the third part is the fluctuation. In other words, if we treat the environment as random environment, then the stochastic equivalence can be captured by the certain fluctuation term. And the second term is the dissipation or the memory term. This term is very important because it tells you the information, how information communicate with the fine grain, with the underlying coarse grain variable and the environment. And the previous deviation is for ODE, and for our SDE, overdamped long-drawn dynamics. Under mild assumption, if we treat the Brownian Brownian motion as some external force, we can get the Zwanzig formalism for the coarse-grained variable by this equation. And the blue term is the effective term, and the green term is the thermal term, and the red term is the memory term. And under some mild assumptions, we can throw away the divergence term and only keep this term. And so if we have a close look at the Zwanzig formalism for this coarse-grained variable G, we can see that these red terms tell us the error committed by replacing the evolution of L by the projected revolution PL. And so on the other hand, we see that this formalism is actually much more complicated compared to the original overdamped long-drawn dynamics. But it is useful for two reasons. Firstly, it can help improve the sampling, and it helped correct dynamics. And I also want to mention that this memory term, the red term, looks very complicated. And the thermal fluctuation term is also very important and equally important when considering the performance of coarse-graining. And here, our study only concentrates on the memory term, but like I mentioned, this term is also very important. Even you got the memory term, say, fitting very well, but if we forget to carefully analyze the fluctuation term, we still cannot get a very good result. Okay, so, and in this talk, I'm going to talk about how to approximate the memory term. This depends on the time of relaxation. So for short time relaxation, we can approximate the memory term by, for example, delta approximation. And for long-term relaxation effects, we have various approximation techniques. And I'm going to focus on the first short-term relaxation effect. And the example here is a very simple two-dimensional potential, which is given here. And you can see that this, the energy, for this energy, there's no energetic barrier because we only have one local minima, but it has entropic barrier because the dynamics have to follow this very twisting pathway, okay? And we have first approach is to, because you can see that if we choose omega, if we choose lambda large enough, then the X2 will very quickly relax to the slow manifold. That suggests, okay, we can choose our coarse-grained variable to be X1, the slow variable, and then we apply the Zwanzig formalism with respect to this projection, and we can get, we first compute the effective potential, and then we subtract the effective potential from the 4 MD to get the orthogonal dynamics. And based on the orthogonal dynamics, we can apply the formula for the memory kernel to compute this memory, to compute the memory term. And you can see that this memory term is very complicated. And because we assume there's a time separation between X1 and X2, one easiest approach is we ignore the time dependence. In other words, we can assume this memory term will relax very fast. and we can approximate this memory term by this delta approximation. But I would like to point out simply discard all time effects will give us poor results, and we need more careful asymptotic spatial calculations. And what that means is, okay, if we plot the empirical memory kernel, and we can observe that, firstly, this memory kernel decay very fast, and secondly, because the x-axis is the x1, and you can see that it oscillates a lot. That's the reason why we have to carefully apply the asymptotic spatial calculation. And the idea for this simple projection is simple. So we compute the orthogonal dynamics, which is given in this, and we assume that for the orthogonal dynamics, the y direction is exponentially relaxed to the slow manifold, and meanwhile, the x direction keep fixed. And then under this assumption, we can get, you can imagine this, this approach give us a first order correction to the previous delta approximation of the memory. And then we can get this equivalent dynamics for under Mori-Zwanzig and the delta approximation of the memory kernel via the asymptotic analysis along the slow manifold. So we will compare this equation, that's only the effective dynamics, with the Mori-Zwanzig equivalent dynamics and delta approximation of the memory. And we turn on the temperature to a moderate region, say beta equal to 10 and beta equal to 100. And we can see that the Mori-Zwanzig the formalism can capture the full MD for X1 very well. Whereas if we slow away the memory turn, in other words, the communication between X1 and X2, then we will get the round dynamics for X1. So this is the Mori-Zwanzig under simple projection, project to the underlying coarse slow variable X1. But there are some challenges because we have thermal fluctuation because we are talking about SDE. Therefore, in some cases, for example, if we start from X1 equal to 0.1, you will see that actually X1, X2, the trajectory of the full MD, they do not very fast relax to the slow manifold. In fact, they oscillated around the slow manifold, and we can compare the full MD with Mori-Zwanzig with simple projection. We see, okay, the Mori-Zwanzig with simple projection cannot capture the true trend. This is because we neglect the thermal fluctuation in the previous case. Therefore, we cannot capture this oscillatory behavior. And in order to take this oscillatory behavior into account, we need an improved projection. So let's record the MD underlying over down to Langevin, and we assume the potential looks like this. And this tell us a slow a manifold which is close to the exact slow manifold. And the idea of the improved projection is we define the Mori-Zwanzig projection along the normal of the slow manifold. So in other words, we suppose the observable at time t is the mean position on the manifold, and then we can estimate the position of x and y along the normal direction by assuming that the true dynamics oscillate symmetrically with respect to the slow manifold. Okay, so in other words, we have the mean position of our observable on the slow manifold, which is denoted by A and Y star. And that's the true MD XY. And then we can estimate the true position of MD by the mean position of manifold plus the perturbation along the normal and along the tangential direction. And graphically speaking, this green line is our slow manifold, and our true dynamics is oscillatory along the slow manifold. And we can assume that this oscillation is obeying the Gaussian a normal distribution. And under these assumptions, we can obtain an improved asymptotic spatial analysis. And then we can compare full MD with Zwanzig with simple projection and Zwanzig with improved projection in these two examples. So here we turn on the temperature again, and we average the samples for 4,000 times. You can see that the improved projection can kind of capture the true MD compared to the MZ with simple projection, which cannot capture the trend very well. Okay, so I may run out of time. Let me finally conclude my talk. So in this talk, we applied the Zwanzig framework for linear coarse-grained mapping to describe an underlying overdamped Langevin dynamic system. And this approximation of memory kernel depends on the time separation. And we also point out that delta approximation of memory is not enough. We have to also take a very careful asymptotic spatial calculations into account. And in order to perform the asymptotic analysis, we can choose a slow manifold and apply the analysis along this slow manifold. And the third observation is we need to improve the projection compared to the simple projection because in SDE, the thermal fluctuation will bring extra challenges. And that's all for my talk. Thank you for your time and attention. Yeah, thank you.
Thank you, Helen. That's a very nice talk. So I guess we probably have a couple minutes for if anybody has a quick question or two.
Yes, hi Xingjie, may I ask a question about your improved projection? Over there you have this N, you have the introduced extra parameter A, that's extra direction basically. How do you determine this A as, I mean, as that's the mean, and then how do you determine this NA and TA? And
it's a very good question. In fact, in the implementation, we assume we kind of coincide A with X. In other words, we still observe X instead of the mean position on the manifold. And because the projection is no longer onto the X, it's onto the normal direction. So it still brings some benefits with this improved projection.
Mm-hmm. And how about the NA and TA?
So NA and TA, we have formula because we know the expression of fx. So we have the analytical formula for NA and TA. When we don't know the expression of the slow manifold, we probably need some sampling scheme to sample the normal and the tangential direction.
Okay, I'm gonna continue that. How does this one relates to this memory MS, the kernel? How do you put this memory part? Just plug in the A as X deleted coordinates?
So because if we have better estimation of X1, X and Y, then we can compute the memory kernel with higher accuracy. So that's the formula for the memory kernel. And we need to insert the XY into the expression. So all we done is we improve the accuracy of the XY, and then we can improve the accuracy of the memory kernel.
Okay, thank you.
Let me see. So there's a question in the Q&A about from Simon Berman about extending this to non-gradient SDEs. You give a 10-second answer.
Oh, it's a very good question. Yeah, so my short answer is we don't know how to extend to the non-gradient SDE at this moment. So this is because in our approach, we assume the Brownian motion, we treat the Brownian motion as the external force. And therefore, we can still borrow the same framework of Mori-Zwanzig for ODE to this SDE. So we don't know how to extend to general SDE. Thank you.
Thank you, Helen, for this very nice talk. So